Okay, welcome everybody. It's a great pleasure to present Piotr Kowalski. Piotr Kowalski is a professor at the University of Wrocław, and his research interests lie primarily in model theory of algebraic and geometric structures. In particular, he studies model theory of group actions on fields and model theory of fields with operators, and so-called X-Schanuel property, which is related to the exponential function, because we mean a generalization of the exponential function to algebraic groups. And he proved that this property holds for many homomorphism of algebraic groups, in particular when the underlying field is of positive characteristics. And it was for the first time, I mean, for the first time that anybody considered positive characteristics in this problem. Piotr obtained a PhD in 2001 at the University of Wrocław. Then 8 years later, his habilitation. And finally, a year ago, he got the title of professor. It's a scientific title, which is very prestigious in Poland. He was a postdoc or visiting professor at Urbana-Champaign, in Lyon, in Paris, and in Oxford. He received a number of grants and awards for his work, and he is also interested in the climate change. He is an official representative of our department in the university panel for climate change. Please, Piotr, the Zoom is yours, please.
Thank you very much for this introduction, and thanks for inviting me to give a talk here. I am sorry I cannot attend in person. This is the first week my daughter goes first time in her life to the kindergarten, and that was also the reason that I couldn't attend many of these talks, even online. Okay, but I'm very happy to give this talk. So let me share the screen again. Okay, can you see the screen properly?
Yes, yes.
Okay, good. Okay. So the main point of my talk is just to give a bit of insight or flavor to the kind of mathematics I am working on, which was in Eva's introduction. And it would be hard to do anything very precisely with all formal definitions. So I want to actually use one particular model theoretic concept, which appears almost everywhere in many model theoretic works, including mine. So the title is about it. So, what does it mean? Okay. So we have algebraically closed fields, which are special kinds of fields, kind of the best ones, the largest ones, when all the polynomials, non-constant polynomials, have roots. So this concept, using model theory, can be generalized from the class of fields to any other reasonable class, like class of groups, rings, etc. So one could talk about algebraically closed groups, algebraically closed rings. But let me warn you that actually this terminology was a bit used in the 70s, but it's not used anymore. I still put it to the title so that it gives some intuitions, but the correct term would be existentially closed structures, and I will get to that. Okay, but my point is that using this concept of existentially closed structures and then a model companion, I want to give some introduction to model theory of algebraic structures itself. Okay, of course, if you have any questions, please interrupt me anytime you want. Okay, so the plan is first I will give quick introduction to model theory in general. Then I will give quite a precise definition of this existentially closed structures and model companion. These notions generalizing the notion of algebraically closed field. Yes, you should have this example in mind to guide your intuition. And then I will give some examples and applications. Actually, applications will be mostly just names. It is a bit hard to describe them precisely in such a short time. Okay, but at least I hope it will give you some flavor again. Okay, so we start from general introduction, very, very general introduction to model theory. Okay, so first, if you want to place it somewhere inside larger branches of mathematics, so model theory is a branch of logic, formally. So the name was given in one papers of Tarski in 1954. He used a term, the theory of models, and it became model theory. But the actual work, I think, was initiated in these topics by Tarski when he was still in Warsaw in 1930s. Okay, then number of people worked on it, and I cannot name them all here, so I'm focusing on two of them, which is, I think, not a very controversial choice. So I'm saying that model theory as it is now is shaped mostly by ideas of Scheller, mainly from 70s. There were ideas from so-called pure model theory. The aim was very ambitious. Scheller kind of wanted to classify all possible theories, and to some extent he succeeded. And on the way, he developed lots of dividing lines, telling you when the theory is complicated, more complicated, and less complicated. And then Hrushevsky and others noticed that these abstract dividing lines have have a lot of, well, actual practical mathematical content. So then Hrushevsky was also applying those ideas of Scheller to concrete mathematical structures and proving new theorems outside of model theory. And that was happening from 80s, and it's happening very much right now. Okay, so now I'm just giving some particular names of other branches of mathematics that model theory has connections with and is applied to, and also vice versa, actually. There are just interactions between them. And so this is like Diophantine geometry, so geometry related to solving Diophantine equations. Yes, Diophantine here means that we are interested in rational or integer solutions. Okay, algebraic geometry in general, algebraic dynamics, okay, differential equations to some extent, recently combinatorics, and more. And I will tell more about it at the end. Okay, so this is the general picture. Okay, so
may I have a question?
Sure.
So you mentioned this application of model theory in differential equations. I cannot imagine.
Okay, I have one at the end. But maybe it's not exactly. I will discuss it hopefully in about 30 minutes. If I don't, please remind me, but I have it on my slides. I prepared it.
Okay.
Actually, it was quite striking. But okay, depends probably what people mean by differential equations, but we will get to that. Okay. Okay, but thanks. Please interrupt me. I always feel better when I hear questions and feel these vibrations from the audience, etc. Okay, so that was the slide title, What is Model Theory? Very briefly answered. Second, what is model theory about? Okay, so very briefly, it's about definable properties of structures. Okay, but where the terms definable and structure have a very precise meaning, which comes from the first order logic. And I was lucky to listen Mirna Giamongia's talk, and then I noticed she also touched these topics. So this is as in her talk, it's the same meaning. I will give some example what what's that in the next slide. I don't have time to define this precisely. And also this first order assumption sometimes may be relaxed, but I will not be getting into that. But actually, what is interesting and really useful that sometimes, okay, usual logic has two true values, 0, 1, but there is a meaningful version when true values are entire compact interval from 0, 1 called continuous logic. There is model theory related to that, and it also recently has connections. This is work of Yakov and Kowalski to the theory of global fields and algebraic geometry. So actually, but I'll also not get into that. In my logic, will be also true value 0, 1. Okay. So what's happening? We always start with fix some language. I will tell by a way of example what is a language for me. And then we construct from this language like formal string of finite sequences, which gives us formulas, sentences, collections of sentences are theories. Then we have structures, some sets with extra structure related to language, and some of the structures become models of theories. Okay, and formal definitions would took several hours, but I will just actually one example on the next slide, what it means. Okay, this example should be enlightening. I take the language of rings, which has, I will write something on the slide later. I hope you can see my cursor moving. So it has two formal binary function symbols, plus times, one, let's say, unary function symbol minus, and two constant symbols 0, 1. Using this and usual logical symbols, quantifiers, implication, negation, conjunction, disjunction, brackets, we construct in a meaningful way, which is, I don't know, I guess everybody can intuitively guess what is a meaningful formula and what is not. For example, if it was only x plus x equals, and if there were nothing on the right hand side here, it wouldn't be meaningful. Okay, but those are meaningful ones. And then sentences are those formulas where all variables are quantified. So okay, maybe it's time to write a bit. Okay, so what I wanted to say is that first, so here I have binary, not much visible, but unary function symbols, just the symbols. They don't have any meaning right now. And these are constant symbols. And formulas are finite sequences. Finite is very important. Of symbols from this language, finite, meaningful. It has a proper definition, but it's syntactic and very long. Sure, yeah.
Is this like an just first order logic with an algebraic structure, and
this is first order logic. It is first order logic, yes, but I also allow, but not here, we allow also relation symbols. Okay, so I guess it's not restrictive to algebraic structures, but in all my examples, there will be only function symbols.
Okay, okay, thank you.
Okay, but formally, of course, model theory allows also relation symbols. I didn't want to make it too complicated. So formulas are just finite meaningful sequences of symbols from this language, and like brackets, quantifiers, And meaningful, I didn't define, can be defined, but also intuitively. It should be clear. And now, sentences are those where all variables, I guess you see what are variables, okay, variables, also x, y, etc., are quantified. So this is a sentence. And it has also, okay, formally it's a string of symbols, but you can guess the meaning. It says that each element has its square root. Yes, for each x, there is y, such that x is y times y. So these two are sentences.
And excuse me, can I have a question?
Sure, sure.
And this language talks about a specific ring or about rings in general?
So rings, okay, even less than that. So far, so okay, good question. So far, it doesn't talk about anything. Okay, up to this part, which I'm now cycling, it really doesn't talk about anything. It is just formal finite sequences of the symbols and collections of them. What is the meaning? The so-called syntax, I guess, and then semantics come here. Okay, so soon I think I will answer your question a bit better. But okay, but I guess the answer is about all rings and even more. Okay, but I think when I will be talking about structures, the answer will be better. So just let me tell you that theories are any sets of sentences. So for example, as in algebra, you can write the theory of commutative rings with identity. Yes, what we are writing are sentences like this, using plus times. Okay, usually 0 and 1 are not, but you can put it to the language and minus as well and express everything, all the axioms of commutative rings with unity, theory of fields. Yeah, so here the axiom of x. So, example of one axiom for which x is to y, such that if not x is 0, then x times y is 1. Yes, that's example. This example of a like sentence, which you add to the theory of rings with 1 to get theory of fields, and also the theory of algebraically closed fields you can express. The difference is that for theory of algebraically closed fields, you need infinitely many sentences. Yes, because you have to kind of cover all degrees of polynomials. Okay, maybe I will not lose time on that. And maybe now getting to the last questions. So far it was only syntax, just sequences of symbols, that's all. Now the meaning comes. So structures, what is an LX structure, is arbitrary set together with arbitrary two binary functions. So binary means from m times m to m. So operations, yes, operations with two arguments. One unary functions from m to m and two specified elements. And that's all. So this is, so you may say that this language, now I'm really answering the last question, talks about these structures. And they do not even have to be rings. Okay, the name language of rings may be confusing, but LX structures do not have to be even rings. It can be absolutely anything. Like I guess in the first lecture in group theory, you see examples of operations which are just totally random and not associative, etc. So the same here. Everything is allowed. And in all such structures, you can check whether a sentence is true or not, or whether all sentences from theory are true or not. Okay, so the last point is models of theories. So that's exactly, you have some theory, collection of sentences, you have a structure, you can check whether if all sentences from this theory are true in the structure, then we call it a model of this theory. So it becomes a bit tautological. So the models of the theory of fields are exactly those LR structures which are fields. Okay.
Excuse me.
Sure.
May I also ask a little question?
Sure.
So when you are working with the direct product of the set M, so neither M nor the direct product is an element.
This is Cartesian product, by the way, but.
So a Cartesian product, I guess.
Yes.
So, but that's not an element of the language?
No, it's not element of language. So that's a big difference here. No. That's kind of interpretation of the language, okay? So the talking about language finished here, what I'm now circling. And the last two dots are about interpretations of the language, okay? So okay, so a structure, a large structure is a set together with interpretations of the language, of the symbols from the language. That's why this upper script.
So you join two languages, actually.
Okay, depends what you mean by language.
Yeah,
but for me, okay, but of course we are talking in a language, etc. But for me, language has a very specific meaning. It's a collection like this. It's a collection of function symbols, relation symbols, and constant symbols. Let for this hour language be just that, okay? And this is interpretation of this language. So language here has this very precise and narrow meaning, just things like this.
In this example.
In this example, and in model theory in general. Of course, in model theory, yeah?
I'd also like to ask about the last dot. Do I understand it correctly that a model can only contain one specific structure?
Yes. Okay, I didn't have. Yes. You have given a structure, and you are asking whether it is a model of a theory. Like, for example, you have Z, normal Z, so I will not. Okay, this is one Lx structure. It is a model of theory of commutative rings with one, but it is not a model of theory of fields.
Okay, thank you.
Okay. You take one particular structure and then you ask whether it's a model of some theory or not. So of course, each theory has many models. Yeah, okay.
Yes. I was I wanted to go back to my question. So a concrete model is about a single ring.
A concrete model of the theory of rings is a single ring, yes.
Okay.
But model of something, you always say model of a theory. Yeah?
Okay. Thank you.
So actually the name, the very name of the discipline is a bit confusing because model theory, it's kind of, its full name should be the theory of models of theories in this sense. So, there is maybe the confusion can come from meta-mathematical meaning, like of language, and this narrow mathematical meaning, also about theory, etc.
Exactly.
Yeah.
That's
so
my confusion.
Yeah. I understand you very well. But but on this slide, always the word language theory have precise mathematical, rather narrow meaning. Okay, they are not our everyday meanings. They are this meanings. Okay. Any more questions to the slide? Okay, then I will move. I think all these comments will vanish, but no more questions. Okay, I have to do something like. Okay. They didn't vanish automatically, but with some effort. Thanks for all the questions. Thank you. Ask more. All right. So now I want to get to this definition of algebraically closed or essentially closed. I'm doing it in kind of simpler possible way, so it will work for some specific theories. So let us fix arbitrary language. I didn't say what it is. You can guess perhaps. You can think about language of rings if you want. Now we have a chain of structures So each structure is embedded into other structure. In a way, the interpretation of the language is preserved. I will also not say so. In practice, it would mean that each next one is like a subring or a subfield or subgroup, okay? Then always the increasing union has a structure of an L structure, just the union of these interpretations. That's what's happening in algebra and more generally here. But then the theory is called inductive. In the case, if you have a chain of models, its union is again a model. This doesn't have to happen, although I guess everybody saw it in some place that we know that, for example, increasing union of groups is again a group. Increasing union of rings is again a ring. Of fields is again a field. The same for algebraic fields as well. And there is a reason for that, which is a theorem in model theory, which takes like 1 page to prove. I will not show it, that theory is inductive if and only if it can be axiomatized by sentences which have just quantifiers for all exists. Yes, so you think, what is, for example, groups? Yes, you have this axiom for each x exists y, such as x times y is identity element. Okay, so like all the natural algebraic theories are like this, if you think about them. And that's the real reason that increasing union of groups is a group, etc., etc. Okay, so we'll make this general assumption that our theory is inductive. At some point we'll make it. So increasing chains of models are again models of this fixed theory. And for good intuition, you can think let's about theory of rings or fields, etc. Okay, so I'm not.
Can I have another question? Yeah, I have a question. Because when we are talking about the union of structures, structures have those, for instance, with the rings, there was the addition operation. They're like defined in a structure, and like, how is this addition then interpreted in this union?
Okay, but it is only, I talk only in the case when it is increasing union. You know, so okay, you can see
so
example.
Okay. So
like if you take integers and divide by higher factorials, you get basically Q. You know what I mean?
Yes.
Only increasing union. Of course, if it's not increasing, there is no way.
So if I have, for instance, 2 elements, I want to add them, I just look at the
at the level,
the structure that is big enough that contains them both.
Exactly.
So okay, now I understand. Thank you.
But still, you may have such a theory that in this union, it will not be your model anymore. It can happen. Actually, it's best to see in the case of orders. If you look at the orders and orders which has endpoints, then it's not inductive, because of course you can have infinite increasing union of closed intervals, but the union may be open interval. Okay, so in case of orders, it's easy to find example of theories which are not inductive.
Being inductive is the same as the closure undertaking, also not chains but directed, yes, sums. Is it the same definition?
Direct, well.
You have some family which is somehow indexed, and the set of indices is a property that it is directed.
Definitely, if you allow only monomorphisms, then yes. But if you don't allow more, but if you allow arbitrary homomorphism, then I would not be brave enough to answer. But if in your family you have only monomorphisms, then yes.
Okay, thank you.
Okay, any more questions to that? So finally, this definition, pretty abstract. So have in mind algebraically closed. So we say that a model of a theory is existentially closed if any quantifier-free formula which has a solution, this exists X means a solution in some extension, of a model, which is also a model, has a solution already in M. Okay, so some explanations. I didn't define this. This LM means that I allow also parameters. So that I leave to you from intuition, that when you construct the sentences, you can plug parameters from a given structure. So this is allowed. And quantifier free, okay, so there are no quantifiers. So you may think it's like system of equations, maybe negated. Okay, that's a good intuition. So systems of equations or inequations, something like this. This is this quantifier free formula. And then, okay, we want to say that all possibly solvable systems of equations like this can be already solved in M. So what does it mean solvable? That there is some extension of models where it has a solution. Okay, so that's a very natural, I think, definition, basically saying all solvable systems of equations can be already solved in your model M. But formally, it uses this definition, which I wrote. An example, coming back to the thing I was talking in the beginning, if you look at fields, then existentially closed fields, so formally existentially closed models of the theory of fields, are exactly those fields which are algebraically closed. This does not follow immediately from the definition of algebraically closed fields, but if you know what is Hilbert-Nussdalen-Satz, then actually it follows from that. Okay, because here this X may have seven, it's not clear, but this X allows, it's a tuple of variables. So it talks about equation in several variables, possibly, not only one. This is actually crucial. Okay, so that is this concept of, which used to be called algebraically closed, but now is called existentially closed, like a very general, very wide generalization of the concept of algebraically closed field is this concept of existentially closed model of a theory. Okay, that is the first main definition. There will be many examples later. So, any questions to this slide? Yes, actually, in the language of rings, parameters from R, good example of quantifier-free formula is polynomial equation with coefficients where coefficients of the polynomial come from M. That's the good example to have in mind.
Excuse me, I have a question.
Sure.
Here we are talking about like the smallest model that might have a certain property for every. Like,
well, we didn't say smallest.
Okay, but in some sense, some. You know, so the smallest or the biggest. My question is that is this have to do anything with the limit from?
I think the next slide. I think the answers are on the next slide. Okay.
Okay. Cool.
Because actually, also the smallest is a good intuition. So let me see. Yeah, exactly. Okay, so before that, actually, one should wonder whether such things exist at all. And here the inductive assumption comes. So if the theory is inductive, then any model has an extension which is existentially closed. And now I think I'm answering the question also by the way of comparison. So the proof of this theorem is actually even a bit easier than the proof of that construction of algebraic closure of a field. Okay, so how do you obtain it? You just kind of add solutions one by one. And if you somehow enumerate all possible formulas or all possible equations, and then on limit step, you take unions of chains, and by the inductive assumptions, you stay in the class of your models. Okay, so I think this is at least related to the question. And then actually, in the case of fields, actually there is the smallest one, the algebraic closure. So first, it is unique up to isomorphism, and then it is also minimal. So it's really smallest one, like in the previous question. But the notion of smallest kind of refers to this extension. So you start from something which is not existentially closed, and then you're possibly thinking, is there a smallest one containing it, which is existentially closed? So for fields, very much yes. Funny things happen for differential fields, for fields with derivation. There is still something unique up to isomorphism, which is smallest, kind of, but it's not minimal. You can find another one, still isomorphic to it, but properly inside. That's a bit against our intuitions. As for fields, it cannot happen. Any proper subfield of algebraic closure containing a field is not algebraically closed. But for differential fields, such a thing may happen. So did I answer the last question?
Yes. Thank you very much.
Okay, but the main point here was to give you intuition how to construct them and to ensure you that they really exist, and there are a lot of them. Yes, each model can be extended. But in other cases, like field with automorphism, there is no unique one. You have such n extending m, but you cannot find anything unique about it unless you add some more assumptions, but it gets worse, kind of. So finally, I think the main definition, so they exist, but now we want a theory which axiomatizes them, okay? Which may exist or not, and this is often a very difficult problem. So if you have inductive theory T, then we call theory other L theory T star model companion of T, if it exactly axiomatizes existentially closed models of T. So if the class of models of T star is exactly the class of existentially closed models of T. Okay. So that's the important notion. I'm already telling you there is no guarantee that such T star exists. Existentially closed models always exist under this natural assumption of being inductive. But the class of them, as we say, doesn't have to be elementary. It doesn't have to be axiomatized by a theory. And that's the important question, when it is and when it is not. So any questions to this slide? Okay. Examples finally. Okay, examples. Theory of sets. I don't mean any ZFC or complicated things. This is empty theory in empty language. So this is really set without any structure. Okay, empty theory in empty language. So models are pure sets, and that's it. So it has a model companion, which is the theory of infinite sets. Because really what you can say only is that there are more than 5, 10, n elements. Okay, so you have to satisfy that. So existentially closed models of theory of sets are infinite sets, and they are axiomatizable by infinitely many axioms. So the theory of infinite sets is model companion of theory of sets. That wasn't very deep. Now, deeper things. Okay, I was saying that orders, so we have language, which is just one binary relation symbol, and axioms are saying this is linear order. This theory of linear orders has a model companion.
Sorry?
Yes, so what? Yeah.
Just going back to this first example of the theory of set. Okay, I understand that you didn't impose any axioms like in
No, everything is empty. Yes, yes.
Okay, but still, a model of such a thing wouldn't be just empty, or
empty as well, if we allow it. No, model is any set. It's like Galois correspondence. the less the axioms, the more the models. So it has no axioms,
okay, I see.
so it has lots of models.
So a model of a theory is always a set, and the interpretation of this.
Yes. But here we don't have any symbols.
And we don't have any additional symbols, so this is just a set.
Yes,
no,
just a set.
No axioms. Okay.
No axioms.
Right, thank you.
But actually, there is not much to say, yes, in the empty language. You basically can only talk about number of elements, nothing else. So you can only say things which are expressed by pure logical symbols. So this is basically inequality, equality. So yes, having some number of elements is the only thing you can say in this first order way. Okay. So second example. So what can happen in linear order? Okay, you can always say between two elements there is another one. So two vectors always happens. Existentially closed linear orders must be dense. But also you can always say there is always element to the right and to the left to a given element. So to make sure your order is existentially closed, it cannot have endpoints. And it turns out it's enough. So existentially closed linear order is exactly dense linear order without endpoints. This is axiomatizable. So this is model companion of theory of linear orders. Fields are already said. Theory of fields has model companion. Theory of algebraically closed fields. Now important theories for application. Theory of fields with automorphism. So language of rings is expanded by one binary function symbol. An axiom is saying that the symbol is automorphism of the field. Field axioms are already there. This has a model companion, which was used a lot. It's called ACFA. Theory of fields with derivations has a model companion. I mentioned a bit before. So again, one extra unary function symbol saying it's a derivation. So it's additive and satisfies Leibniz rule. So I'm also slowly getting to this application to differential equations. Something more down to earth, theory of commutative groups has a model companion. Okay, what you can say it's divisible. Yes, anything has nth root. So it must be divisible, but also there should be many elements of any possible order. So having infinitely many elements of order P for every prime P. And again, this is enough. This axiomatizes the model companion here. So these were positive examples, now negative, which are a bit surprising. Theory of groups has no model companion. Existentially closed groups exist, but are quite mysterious. And you cannot axiomatize them. You can prove that you cannot axiomatize them. And the theory of commutative rings also has no model companion. My last two slides are proof of this fact, but I will not get to that, I'm afraid. But anyway, I can tell later to people. So this 7 or 8, actually, I was giving a lecture 2 years ago. There were problems in problem session, and after some hints, it's like problem for students. But it requires a bit of mathematics. But anyway, so some questions to these examples.
May I ask a question?
Sure.
When you're talking about the theory, what actually do you mean by this? Because if you say the theory of fields, I'm firstly thinking on the axiomatization. So you have some axioms in the beginning, and you define what the field is. But what is the theory?
So, okay, you are right. I would say it consists of the axioms which you saw in your algebra class, which kind of contradicts the D, because probably people saw different versions. So it's your favorite set of axioms or giving you the theory of fields. Formally, it would be something else. Formally, it would be intersection. It will be all the sentences which are true in all the fields. That would be the formal answer to your question. But what I mean is something less formal. It's your favorite axiomatization of fields, okay?
And what do you mean by favorite?
Don't you have a favorite one?
What do you mean by favorite?
Just according to your personal taste.
Okay. Okay. Okay.
So of course, it wasn't perfectly precise. I would have to write them, okay? To be perfectly precise, I would have to choose these 10 axioms and write them on the slide, but it would be too much.
Okay.
Okay. Okay.
Thank you.
You're welcome. Okay, any more questions to the slide?
Yes, I wonder if you can, maybe it's not about slide, but like about model theory in general. If you can maybe use the tools from model theory to say something about information theory.
I have not much of the idea, but okay, there's something I'm not doing, but there is something called finite model theory, which I think is done, for example, at University of Warsaw, and I think it has connection to computer science. But I'm really not an expert at all in this. So, okay, my answer is I don't know.
Okay, thank you very much.
Any more questions? Okay, maybe I will move this slide. Okay, so what's the natural model theoretic attempt to study some class of algebraic objects, model theoretically? I'm saying as fields with derivation or commutative groups, some axiomatizable class. It's natural first to check if model companion exists. And if it exists, it's usually kind of nice theory. Nice, I'm not defining yet, but it usually nicely fits in the Scheller hierarchy I was vaguely mentioned. It's kind of, there are some tools to be applied to this different notion of ranks, analysis, some kind of general geometric analysis of definable sets. And using this, so analyzing model theoretical properties of such theories, you can get applications, concrete mathematical applications. So I want to just give some of them on next slides. So this was just to give a feeling what is the starting point to do something particular in model theory of some algebraic structures, for example. Usually it's about algebraic structures. Okay, now I can answer the question about differential equations. So first, DCF0 is now I'm saying the model companion of the theory of differential fields of characteristic 0. So this theory has all the axioms of fields, your favorite ones, axioms of characteristic 0. Actually, there are infinitely many axioms, yes, saying 1 + 1 is not 0, 1 + 1 + 1 is not 0, etc., etc. And saying that your unary, extra-unary function symbol is a derivation. So this theory has a model companion. It's a very nice theory. There are nice ranks attached to it. And there is some geometric analysis of it. So first, it was used by Kowalski. Actually, it was first application to the affine-time geometry, something called relative model length. But quite recently, it was used together with some mixture of other results by Kazal, Freitag, Naglu. So as they say, to give a complete proof of an unproved assertion of Paul-Levé from 1895, so from 19th century. So what was this assertion? Okay, the assertion was about what he called irreducibility of differential equations. This is something like, okay. Yes. If I remember correctly, if you want to integrate such a thing, you run into troubles since it's not expressible by elementary or special functions. So Paul-Levé have this notion, he didn't give a very precise definition of irreducible differential equations, by which he meant that no solution of it can be obtained from some elementary function like exponential polynomials, the logarithm, etc., etc., etc. And he gives some, and he claimed that some particular differential equations are like this. And it was first time proved using model theory of differentially closed fields, as the CF0, by this paper by Kazal, Freitag-Naglu, which appeared in Annals of Mathematics. So this kind of differential equations, I don't know, maybe it's a bit old-fashioned. I'm not really sure. I have a feeling that now people are more interested in particular solutions of differential equations, like how smooth they are, etc. So for such things, I don't see much applications of model theory, but for questions like whether the solutions can be obtained from elementary functions, that very much, this actually exactly corresponds to some model theoretical notions. So did I answer the question from the very beginning about applications to differential equations?
Yes, thank you. I'm happy.
Okay, so that was this. Still fine kind. Okay, maybe. I don't have time to explain. It's also a very nice idea. Maybe very quick.
Well, Piotr, you may go a little bit over time because there is a lot of discussion, which is very nice.
Okay. Okay,
So
so let me. Okay, thank you. So this is your fine time because it's a very nice idea. Okay, so your fine time. So I don't know. You want to let me start. You want to solve such an equation, let's say. Which was definitely not done by model theory. Okay, but what is it? This actually, okay, so if you divide by z, so actually you are interested in rational points of a curve given by, yes, if you divide by the z, instead of solutions in z, you are interested in solution in q, this curve. So you have this curve C, let's say. You embed the curve, you can embed each curve to so-called Jacobian. This is some commutative group with algebraic structure. You have a structure of algebraic group. And then you know that the set of, okay, here you have something called, okay, maybe it's too technical at the end. These are rational points of this Jacobian. It can be shown this is finitely generated group. So in fact, to solve the finite problem, you are interested in intersecting, let's say, curves in some algebraic groups with finitely generated subgroups, so-called arithmetic groups sometimes. And this is very difficult. But what Hruszewski, what first Boyum actually had the idea, and then Hruszewski, he can embed this arithmetic object in some group definable in DCF0. You can embed this finitely generated group in a group which is not algebraic, but kind of living somewhere in between, living in this theory of differentially closed fields. And then you can treat it model theoretically and obtain some results. Okay, probably it was a bit too much, but this is like a general picture how model theory was used to kind of define time problems, which are really, these define time problems, when they are stated, are really about intersecting finitely generated subgroups with subvarieties. Okay, but it's motivated by this example. Okay, and the beautiful idea was to replace this wide finitely generated subgroup but something a bit better behaved, this group in between, which is defined in terms of first order logic, but in a richer theory, which also involves derivation, for example. And then there was a positive characteristic version of it, which is on the next slide. And this was actually the first big application, well, for which Kowalski almost got Fields Medal, but at the end he didn't, unfortunately, in '98. But this was the first. Quite surprising for people that there were such connections exist. Okay, sorry, this was a bit vague. Any questions to the slide? Oh. Sorry. Okay, so some more examples like this. So I mentioned this ACFA. This is actually very interesting, a bit more difficult. Somehow model theoretically, automorphism is much more difficult than derivation. Somehow it seems like easier concept, but it's kind of more complicated. So using this model theoretic properties of ACFA, model companion of fields with automorphism, Shasidakis, Kowalski, and others also found like similar way applications of affine geometry, but also algebraic dynamics. If you have consider polynomial function, then compose it with itself, look at orbits, where they are dense, not dense, it's related to many other problems. It can be attacked from this using this model theory of ACFA, basically. Then theory of valued fields. Okay, there are several different ways how to formalize it in a first order way. You can just pick one unary relation, so it's just a subset for evaluation ring, or you can consider different sorts, which I was not talking about, but anyway, it is doable. The theory of valued fields has model companion, which is actually just theory of algebraically close valued fields with non-trivial valuation. This is enough to be said. And it was used by Kowalski and Kazhdan, algebraic geometry for motivic integration. Yes, I will not explain any of these things. And also by Kowalski with Lezer to solve some open problem theory of Berkovich spaces. And from a bit another direction, more analytic, you have the theory of ordered fields. Yes, order should nicely respect, or addition multiplication of the field should respect the order. It has model companion, which is real closed fields. Of course, the main model is the field of real numbers. Okay, it was used for like this. It appears in non-standard analysis, but also some time ago, Pila noticed this connected to transcendental problems. And then Pila Wilkie showed many transcendence results using methods coming from this model theory related to this RCF. And recently it was announced that the long-standing open conjecture, under-ordered conjecture, was proved using this and other methods by Pila and the others. Okay, maybe just last slide, so something about myself. So as I was setting, okay, first, a funny thing, which very difficult to prove. So Kowalski showed that actually, okay, so theory of fields with one automorphism has a model companion. Theory of fields with two automorphism, or 3 or 5, also has, but theory of fields with two commuting automorphism does not have a model companion. Very surprising and hard to find intuitions about it. Okay, what is fields with two commuting automorphism? If you think a little, it's the same as action of the group Z times Z. each generator gives you one automorphism, and the fact that they commute with each other, generators of this abelian group, means that these automorphisms have to commute. Okay, so fields with two commuting automorphism are exactly in natural one-to-one correspondence with actions of the fixed group Z square on fields. So you can ask more generally, for which fixed group G, the theory of actions of this group G on fields has a model companion. And this turns out to be a very difficult problem. So I have some results with my student Daniel Hoffman, and separately with Özlem Beyarslan. Okay, there are several results. As an example, so usually they are not full. It's very hard to give some kind of if and only if classifications, but we managed in the case of commutative torsion groups. So we found the algebraic criterion on a commutative torsion group, which is equivalent to the logical thing, saying that if you fix this group, then the theory of actions of this group of fields has a model companion. So kind of on the one hand side of the equivalence, you have logic, on the other algebra, and it's a full characterization. Yes, so for example, we did such a thing. So any question? Okay, so I'm stopping here and I'm happy to hear any further questions. Thank you.
We are clapping. I don't know if you can hear. Anyway, thank you very much for a nice lecture. And maybe there are questions. Yes, please. Take the mic, please. Okay.
Okay, so I was wondering about, there was this example of groups on one of the first slides. So
no.
I'm not sure if I understand this correctly, but I was thinking about that, and I think that, is it true that all possible theorems, properties, sentences, I don't remember how it was called, in this theory, these are just all possible relations in like these are only sentences like xy equal to 1 or
something like this, but of course but you are asking about language of groups, or
yes.
Okay, so let me more or less. Okay, but they are well. Okay, of course you can say now I'm. Let's say for RZ. Okay, I'm not sure if this makes any sense, but something like this. But actually, they may get very complicated in a way. But yes, you just have the language of groups. Okay, language of groups is usually taken as plus inverse for some reason, and let's say this. So one binary, one unary, you don't have to take it, and one constant. So whatever you can compose with this.
Yeah, okay, so actually I can see why my first question, like why it didn't make sense, but anyway, I have another question. Could you maybe provide us, is there like an easy example or maybe an understandable example of a group which is existentially close?
No, unfortunately, that's the main problem. Okay. But look, for example, so answer is no. But for example, for fields even, we have only one natural example of algebraically closed field. Yes, complex numbers. Actually, there is no natural example for differentially closed fields, although they exist. it's a formal process of getting them, but there are very, very rarely, at least in algebraic case, natural examples of them. So it's like universal domain in which you live, but actually except complex numbers, there are not many. Okay, you can, for commutative groups, you can just take some direct products, but somehow one should not, of course, you can also see infinite sets. That's okay, and for second one as well. But in algebraic cases, you should not expect natural examples, unfortunately. So no, they exist, but by this. And of course, the axioms of choice is in the process, kind of. So yes. So I'm sorry, but I don't think any natural example is known, and probably in a way it may not even exist a natural example of existentially closed group.
Okay, thank you.
Okay. Any other questions?
May I ask a totally stupid question?
Please.
I'm staring at these points 6, 7, and 8. And I'm reading about the theory of groups, the theory of commutative groups. So how about the theory of quantum groups? If I would take the theory of commutative quantum groups or abelian quantum groups, it exists, would it also have a companion? And the theory of quantum groups wouldn't have a model companion?
Then I would have to know what a quantum group is. What is quantum group?
Well, I mean, read Voronovich and then.
Piotr, I think that I can answer the question.
Perfect.
So, unfortunately, all this, everything which is analytic does not fall into this realm of the first order logic.
But maybe, okay, so if I see a mathematical definition of quantum group, I could think whether this can be axiomatized, but then the hope would be that it continuous logic, maybe it fits to the first order continuous logic, maybe, but first I would have to see, okay, is quantum group some special Hopf algebra?
Well, that's the algebraic backbone, like the Peter-Weil theory. But Adam made a very good point. When you talk about quantum groups, you really speak about topological quantum groups. Okay, there is this continuity aspect there, and then in the case of compact quantum groups, we have this Voronowicz Peter-Weil Hopf algebra, so you can sort of reduce it to the algebraic levels. Okay, so let me rephrase my question.
Can I interrupt you for a while? Sorry, but even Hopf algebras formally do not fit here. Yes, because
that's exactly what I had to say. Yes.
So okay. you would have to use some tricks how to understand like I don't know what's the word, because you have usually operations or something taking x, y and producing z, but in Hopf algebra you have something opposite. So already this doesn't fit. Maybe with some tricks. Yeah, I don't know actually what would be modeled.
Also one possible problem is that after all, everything is taken over some ground field. So this
ground field you can add to the language. That's not a big deal. Okay, problems with topology maybe could be done with continuous logic, but okay. Honestly, I have no idea.
But you say that only for Hopf algebras it is a problem. Yeah,
but I think that could be overcome somehow.
Okay, because then it'll be interesting to see if the theory of all Hopf algebras has no model companion, but the theory of co-commutative Hopf algebras does have.
Okay, I will have it in mind. Because actually I was doing. Okay, so I'm not sure how much is related, but I was working with group actions on fields. But also it makes mathematical sense to look at finite group scheme actions on fields. And finite group scheme is exactly some kind of finite Hopf algebra.
Exactly.
And their actions on fields actually correspond to things like Hasselschmidt derivations, and they can be axiomatized. Okay, so not algebras itself, but their actions can be axiomatized. Maybe also care about actions, I'm not sure. So, okay, so that's an example where it can be. It's okay. So there are ways to approach things from first order perspective, but I don't know about Hopf algebras themselves. Maybe
there is some hope.
Okay.
There is hope. Yeah, there is hope.
Okay, so Piotr, you may incorporate him into your project because Piotr is from Wrocław.
Yes,
Okay,
of
why
course.
not?
Okay.
There is, you know, Piotr, there is a big European project, yes, a lot of money for collaboration, and Wrocław is a node in Piotr project. Okay, so, well, I noticed that there is a question on Zoom, but
Yes, from Frank, yes.
Yes, Frank, maybe
Yes,
you can
it's very similar to the discussion which just dropped in. I'm thinking very similar. So my question is this related to the inductivity assumption that model companions exist because of the inductivity assumption?
Okay. So I said I was giving simpler definition. There is a more general notion of model companion, which does not use this assumption, and is not so much related with existentially closed models, not necessarily. But in reality, for me it is. So it is morally, so formally not, but morally yes, I would say.
Because then I would ask, does there exist the theory of normed spaces?
Which spaces?
Of normed spaces.
Normed spaces,
And if this theory exists, does it have a model companion?
I think it, okay, but I think this theory normed spaces. So of course the problem is that the values of the norm are in real numbers. So this actually exactly fits to this realm of continuous logic. And actually it's a problem because the value set is not compact, but there are tricks for that. Okay, I would have to check. My guess is yes. I would have to check because I'm not doing continuous logic, but I think it has. But okay, I would have to check later.
And
so Itai Ben Yakov was doing such things like earlier with Hanson. They were actually exactly doing, okay, they were doing model theory of Banach spaces.
Exactly. Yeah, that's my question. So whether the model companion then is involves completeness.
Okay, but I'm a bit outside of my area of confidence.
I do not know anything about that, so thank you. Yeah.
So before I can check and tell later, but out of the top of my head, I don't want to say anything which is false. But definitely it was studied, and my memory kind of tells me that it exists, but I have to check.
Perhaps by guys like Ziegler from Vienna, perhaps, yeah, maybe.
That I'm not sure. Okay, so definitely this continuous logic, and main example for a long time was Banach spaces, was done by mostly Itai Ben Yakov and others, who is a logician.
Okay, thank you. Interesting. Yeah.
Okay, there's one more question on Zoom. Arthur, please.
Yes, I wanted to ask again more about model theory in general, because we were talking about this first example, the model of rings, right? And the models of rings are just certain rings, and can we, like, in model theory talk about, for instance, homomorphisms of rings, like something that goes between the models?
Yes, there is a general notion of homomorphism just between structures, LR structures. So it should, the natural one, okay, especially if you don't have relation symbols. Yeah, it's like homomorphism between groups. Because, okay, the notion of homomorphism, for example, for groups, you don't use the group axioms even. You just use that the operation is preserved. So the same in any language, more or less. So yes, there is a general notion.
So in model theory, there's a general notion of like a morphism between structures.
Yes. Okay. So I think there is, yes, like I would say L homomorphism. So okay, definitely there have to be structures with respect to the same language. Okay. Okay. And then there is a notion. I mean, several versions, but yes, there is.
Okay. Thank you.
Okay, any other questions? Please, Adam, please.
And yes, I would like to ask a maybe crazy question, but does it make sense to talk about a model companion for ZFC itself?
Yes, that's a bit correct. I know, but it's okay. Yes.
Like that, you take a chain of models, but models of the whole ZFC. Like
of course, yes, but this
yeah.
is again, of course, we cannot construct. It makes sense. I have no idea. My guess would be it is not inductive. We should look at the axes. For anybody remembers, are axioms of ZFC in the form of for all exists? I guess not.
I'm not so sure.
So my guess would be it's not inductive. If it's not inductive, then there may be no existentially closed models at all. Okay, so this approach would not work. The general definition, I don't know. The general definition says that it should be theory which is model complete, which has some proper meaning, which is closely related to the original theory. Yes, but then it's okay. Well, so wide and a bit funny answer that maybe this question is independent of ZFC, but it's mostly a joke.
Okay, I have one more question. You mentioned that there is a perspective, for example, by Shellac, that some theories are more difficult than the others. And this is a kind of model theoretic perspective, which for me is an ordinary.
So for example, the ZFC is worst possible.
Worst possible, yes?
Yes, worst. You cannot understand definable set. So already, I guess, piano arithmetic is bad. Already, I think the field of rational numbers is bad. I think Z plus times is already bad, yes. Because
okay, and for an ordinary mathematician, how an ordinary mathematician could see some instances of this fact that some theory is difficult. For example,
I think
if there is this huge theorem of classification of simple finite group, for example, is it somehow reflected in some abstract properties of the theory of groups, that somehow one should expect this complex behavior? Or
that probably not. I don't know. Definitely, some families of finite groups could be treated from the point of view of ACFA, but I think it's unrelated. But maybe I have quite a good example about rational numbers. So rational numbers seem to be as a simple object, but you know there is an inverse Galois problem, which is still open. Okay, and like the absolute Galois group of Q, the group of automorphism of algebraic closure of Q, is a very, very mysterious object, and it kind of can be interpreted in a way, in a first order way, in the field of rational numbers. So that should give some kind of flavor that, okay, there is this very mysterious object, absolute Galois, mathematical object, absolute Galois group of rational numbers. It can be interpreted in first order way in the field of rational numbers, and that's kind of a sign that the field of rational numbers is very bad out of any nice Shellac dividing lines.
Okay, but I do not understand one thing. You are talking about the field of rational numbers. So this is a concrete field, like a concrete model of a theory of field. So this is reflected by, this is related to the fact that the theory of fields itself is complicated from this point of view of Shellac, or do you rather mean that there is like a theory of a rational field analogous, for example, like there is piano arithmetics, which is has to be a theory of natural numbers, but after all, we have some non-standard models of it.
That's a good question. Okay, maybe I was not precise. So theory of fields is not complete. I mean, there are many different fields logically. So rather, it makes more sense to talk about theories of specific fields, like rational numbers or particular algebraically closed fields. Okay, so okay. So Scheller considered so-called complete theories. That means that all models are logically the same, if you know what I mean. And theory of fields is very, very much non-complete. There are fields like fields of rational numbers is very different than fields of complex numbers. Okay, so it kind of doesn't fit. Okay, so to talk about dividing lines between different theories, you have to first assume that theory is complete itself. Otherwise, it covers too many objects at once, and the question kind of doesn't make so much sense. But that's why I go to model companion, that from any theory, I get this nice model companion. So that was also, okay, did I answer? Maybe I...
Yes, thank you.
Well, okay, Arthur, I will allow you to ask a question, but somehow we have to come to the end. Please,
okay,
Arthur,
so it will be a quick one, because I was also wondering about this like morphism between models, but can we like in model theory in some like can we like state some statements, for instance, about all morphisms between models of certain theory? Or is it like beyond this?
Not for, okay. There are questions like, for example, which are also in algebraic geometry, when, for example, when the automorphism group, so the automorphism group of projective space is again algebraic group PGLN, and in model theory you can ask when the automorphism group has some definable nature. So in this sense, maybe. But as such, the set of all morphism is very much non-first order object.
Okay. So in general, no.
In general, no, but there are, okay. So whenever yes, it's usually interesting theorem.
Okay. Thank you very much.
You're welcome.
Okay, I think we should stop. No, I would like to stop the recording now. Ale nie powinno się nagrać. So I will stop the recording.